This is Chapter 9, Problem 48 in your book, which is web assigned number 37, Problem 6. This has to do with a problem that is pumped through a pipe in the Colorado River up to a village that is at the rim of the canyon, and there's a big height difference. So the first question asks you to find the minimum pressure the water have to arrive at the village. All right, what you can assume here is that the minimum pressure will give you a rim pressure of atmospheric pressure. So I know I have to have some sort of extra pressure at a lower level in order to get it up to the rim. That is also assuming that whatever velocity I have at the river will equal the velocity at the rim. And that is a very slow moving velocity for the fluid. So anyway, the two terms that are equal to another would be the kinetic energy per volume terms. So they subtract out of each side, and I come up with a simplified equation. So the pressure required at the river plus 1,000 times 9.8 times the elevation of the river, which is 564, will equal atmospheric pressure at the rim to get a minimum pressure at the river, plus 1,000 times 9.8 times the elevation at the rim. And I end up getting 14.32 megapascals for this number. Now, part B asks you to find speed if you're given a flow rate. The thing here is we're given a flow rate in cubic meters per day. And if we hope to find a velocity in meters per second, we have to change the flow rate to cubic meters per second. So I just do a factor label method. 1 day is 24 hours, 1 hour is 60 minutes, and 1 minute is 60 seconds. And I can convert this flow rate per day to a rate cubic meters per second. Okay, so to find the velocity, I take the flow rate, which is area times velocity, divide by the area of the pipe, and we were given the diameter of the pipe from which we found the radius. So the area of the pipe is circular, and that equation is pi r squared. So I take what we just found for the flow rate in cubic meters per second, and I divide the area in square meters. I find that the velocity is 2.81 meters per second. The additional pressure required really is strictly due to that velocity at the rim. Everything else is the same. So because the numbers were so large before, I've chosen to leave those out of the equation. But whatever additional pressure we need is due to that flow rate. So we found the velocity before. That would be 1/2 rho v squared, or 0.5 times 1,000 times 2.81 squared. And I get 3,948 pascals, which is equal to 3.948 kilopascals.